All right, people, so let's keep going. So we've given details of the basic method that we use in computer vision, which is linear least squares. And then we have given one of the nonlinear extensions of least squares, nonlinear least squares. We've done in detail, or we've seen in detail, the derivations for gradient ascent and gradient descent. And I gave you the derivations for scalars and vectors and matrices, right? And I ask you to do that homework where you extend this to any other tensor of order k, okay? So make sure that you do that homework, and I think it's due tomorrow, if I'm not mistaken, right? Okay. So the next thing that I want to do is to talk about one of the applications of all this into low-level vision, okay? So we're back to low-level vision, and for this we're going to derive or define rather. We're not going to derive the details, but you have the paper as always in Canvas. But we're going to be using a specific deep neural network, which is called a Boltzmann machine, okay? And Boltzmann machines are a very simplistic type of artificial neural networks. And the simplification comes from the fact that the neurons or the cells of that graph that represent that A and N are defined as SIs, variables SIs that are either on or off, or you could say 0 or 1, okay? So they're either 0 or 1, that's it. And 0 stands for off, and 1 for on. So with this, we can define a very simplistic ANN, artificial neural network, such as, for example, the variable zi, it's equal to the total input to that cell, right? So remember that for each cell, you have incoming inputs, right? And because of that, we may also have an additional variable, which is the bias. Right? Right? And because of that, I can write this bias plus the sum of all Sj, right? That come into here, all these Sj's, multiplied by the corresponding weight vector, right? So Wij, which is the weight from J, from the J cells to that ith cell, right? Or ith neuron. So this is a very simplistic model. So again, this is the bias, right? These Sj's, as the ones above, are just zeros or ones, right? They can only be zeros or ones because they are only binary cells. And these are the corresponding weights. And then what do we do at this input? We do g of this zi, right? And then we can use whatever nonlinear function g that we want. And as we've done before, we can use the logistic sigmoidal, for example, which is equal to 1 over 1 plus e negative x. Right? So in particular, the probability then that this cell, this ith cell here, Si is going to be equal to 1, is going to be given by 1 over 1 plus e negative zi, right? Then I have to correct. So if we compute the global energy function, I'll have energy in quotation marks. That means that we sum over all the information that comes into that system. Then we can write this formally, mathematically, as negative I of Si bi minus S the sum of all the si's and sj's for, I'm going to say, every I that is smaller than j, because I have ordered them from smallest to largest, right? And then wij. Make sense? Right? Okay, so we say this energy in quotation marks function because if we note this function actually specifies the total energy of the system, because if I compute the function, the function for Si equals to 0 minus the value of the function for Si equal to 1, then what do I get? If I make the correct substitutions here, I'm going to get Bi plus the sum over j of Sjwij. Am I not? Because I substitute this for either 0 or 1. So it's going to be 0 first, and then 1, and then this is going to be 1, and then the corresponding 1 here. Okay? So I'm going to end up with this original function that I had, right? Which is that same function here. Okay, so this is straightforward. Now let's talk about deep Boltzmann machines, which is where we're interested in. And here we're just going to extend everything that we have done, but for more layers, right? So we're just going to do what we did early on when we started talking about artificial neural networks, that we defined just the input, the hidden layer, and the output layer, right? And now the hidden layers, we're just going to extend and put many hidden layers, right? As we please. Okay, so let's do that. So let's start with the same definitions as before. We're going to start with the definition of the visible or input variables. So let us define the visible, right, or the input units, as we'll define them as V, and V obviously can only be 0 or 1. Let's say that I have capital D of them, right? So I have capital D of them. So I have V1, V2, V3 up to VD, right? Okay, excellent. And therefore, here D is the number of nodes in my graph, right? Or the graph that represents my artificial neural network. Okay. Now, similarly, we can let h of capital, in parentheses, capital L, which capital L specifies the layer number, right? This will let it be either 0 or 1 for FL, where now this corresponds to the layer number. This is the hidden variable that I don't have access to. This is the visible variable that I do have access to, or that it's visible to me. And then for each layer, I'm going to have FL cells or FL nodes in my graph. Okay? So the number of nodes per layer could change. So let this be the set or sets of hidden layers. Make sense? Okay. Now, for simplicity, we will assume, and we'll do that because we want to simplify things as much as possible, at least for now. We'll assume that we only have connections between consecutive layers, okay? And by connections, I mean edges of the graph that defines my neural network, okay? Yes? So I only have edges that go from the nodes of my graph from layer 1 to layer 2, and edges that go from layer 2 to layer 3, and edges that go from layer 3 to 4, and so on, right? But I don't have connections or edges in my graph that goes from layer 1 to layer 3. I don't have those, right? Okay? And because it's feed forward, I don't have edges that go from layer 2 to layer 1, obviously, because that would be going backwards. Okay? So we can now compute with this. We compute the new energy function of our diffusional neural network, same as we did here. And we're going to get the exact same result as we got here, obviously. There's no complication here yet. So we have our function of energy function with respect to V, the layer of visible nodes, the H, which are the hidden layers, and the parameters psi of my network. And this is going to be negative the sum for all the layers from 1 to capital L, let's say, of this, we're going to have another summing term here, I from 0 to F small l, right, for all the nodes that I have in the small l layer, right, of hi of L times bi, right? So same as I had here, I had Si. Now instead I have obviously hi for the lth layer times the bias plus the sum for ij of hi of L minus 1, the previous one, times hj of L, the current one, times the weight between these two, right? So the weight between I and j, okay? I'm going to put L here to clarify and close parentheses. Yes? And now remember that the edges, hi and j can only be 0 or 1, right? So this equation simplifies very quickly. Okay, so in this notation, I have that h0, right, correspond to v, or I could say h0 here, right, for the 0 layer, for the first layer, that correspond to the input information that I know. F of 0, right, for the first layer again, we've decided that we called it d dimensions or d cells. I can have capital H equal to h1, h2, all the layers up to h capital L. So that's my set. And psi, the set of parameters, are my weights, right, which are the wij's for each of the L's, right, for every I, j, and L that I might have. Okay. Now, if I and j are different numbers for each layer, you can eliminate the L, and that simplifies notation. That's actually pretty typical. If you want to keep L there, you can repeat I and j, right? Okay. Now, it is very common for simplicity to assume that our biases are equal to 0. And if you assume that, then the equation simplifies even further, right? So let's assume that, and let's further assume that we only have 3 layers. There would be an input, a hidden layer, and an output layer, okay? And then the extension to more layers, just trivial, obviously. Just increase the number of hidden layers. Now, I say trivially, I mean trivially mathematically. Once you implement these things in a computer and you use gradient descent to actually make that gradient descent converge to an actual solution, becomes harder and harder as you increase the number of layers, okay? That's something that I talk more about in the machine learning course if you're interested. But if you haven't taken that course, be cognizant that that could be an issue, right? So make sure that you read the right papers or books for this. Okay. So we're going to assume that capital L is equal to 3. That's the number of layers. And with that, it can be shown that this graphical model that we have defined here, when iterated sequentially in an order that does not depend on the value of the total input, that converges. So this model converges to a Boltzmann distribution. And because this graphical model that we've defined here, when iterated, converges to a Boltzmann distribution, these are called Boltzmann machines, right? That's where it comes from. And the distribution it converges to is P of V, given the n parameters actually, is equal to, I'm going to leave some space here, the sum over all h of the exponential. Remember, the Boltzmann distribution is of the exponential family. Negative the functional, the energy functional, the energy function that we have defined there before, which is given by V, H1, H2, H3, and phi. Okay. And now here I need the normalizing constant, right? The normalizing constant, remember, is the one that guarantees that if I take the volume under the curve of the PDF of that distribution, that integration or that volume is equal to 1, right? That makes it a PDF. And I'm just going to call these normalizing constant z, some value z, given my parameters. Okay. All right. So that's what this converges to. And we can use that fact to derive the conditional probabilities of our model. And again, just going to give the results here. But I do encourage you to actually do the derivations at home, or at least check the papers online for this, because it's good practice to see where all these things come from. Should be pretty straightforward by now, but obviously if you've taken 8001, 8002, you have done these things in detail, right, in class. So the conditional probability for Hj for the first layer, that is equal to 1, right? Remember, Hj can only be either 1 or 0, right? Given the visible values V and H2, then this is equal to G. Remember, G is whatever function I have decided to use, right? A nonlinear function that I've decided to use. That function of the sum of I from 1 to D of Vi, Wi, J. This would be for the first layer, so I'm just going to indicate the weights of the first layer, plus, what do I have here? L from 1 to F2, right, for the second layer. And now I have H of L. Now, actually, I'm doing this wrong, aren't I? I think I'm doing this wrong. Not L. Let's say, can I use, oh, I already used K. So let's use K, okay? From 1 to F2 of HK, right? Now the case for the Lth, which is going to be the 1 in my case. No, actually the 2, excuse me, for the following one. W, J, K for 2, right? Okay, that makes more sense. And the pi probability of, say, HL of 2 that is equal to 1, given, in that case, H1 and H3 is equal to G of, what am I going to have now? I'm going to have the sum over J of xj of 1, right? I'm not having V anymore, which is the input, but the next layer, which is H1, WJL, and this is going to be a 2 plus the sum over all k of HK of 3 now, right? The next layer times W, or is it LK of 3. The probability of, say, the third layer, let's call it K3 now, that this is equal to 1, given H2, just the previous input, this is going to be equal to G of, okay, anyone, what's this equal to? If I have only now considering the input of the previous layer, and I'm computing the probability of taking H3 equal to 1, what's this equal to? The sum over all, say, L of H what? HL of which one? What's that? Speak up. 2, okay, right? Times W from every L to K, right? And one more, the probability of VI given H1, that is going to be equal to, or B1 equal to 1. This is going to be equal to G, the sum over J of XJ1, Wij1, right? Anyways, you can derive the conditional probabilities, which are nothing else than given the different parameters, either parameters or observations or hidden values, right? You just compute the equations that we have derived. Now remember that in our case, we have assumed that, or we have decided that we're going to use the logistic regression function, which is 1 over 1 plus e to the negative x, right? So if we now want to minimize or maximize this probability, right, this conditional probabilities, then we need to compute the partial derivative, right? Because we want to compute the maximum likelihood estimator, right? Unfortunately, this is an intractable solution, and we should know that by now. And instead, we're going to use gradient descent, right, or ascent. Okay. So remember that our goal, as per usual, our goal is to find a set of weights. So our goal is to find a set of weights. And you could include biases. If you're considering biases, then the weights and the biases, obviously, that maximize the probability, right? That maximize our probability function. And that probability is given by the training samples, right? The observations. Okay. Now we can do this by writing the partial derivatives. So we can write this as the partial derivative of the log of the probability function divided by the partial with respect to the weights, the parameters, right? And I'm going to sum this over all the v that it's in my training data. Actually, we call this training data, I think, capital X, this weird X, right? Our data. It turns out that these derivatives of the log likelihood are equal to the difference of the expected values. So you can actually compute this as the expected value of the data, right? Or again, if you prefer, you can write here the expected value of X, or the data, where you prefer, of HL minus 1 times HL minus the expected value of the model. Let's call it capital M. The model is what you have learned, right, of HL minus 1 times HL. Now, here, the first expected value, right, with respect to the data, this one right here, computes the expected value over the training samples, right, the given data. And this with respect to the model, M, right, or you could call it, if you prefer, it's whatever you want to call it. You could call it A and N, or you can call it the model, or you can call it the Boltzmann machine, right, and so on, right? Specifies the current model as it is known right now, and as it's trained right now, right? So obviously, that should be pretty obvious by now, that what we do is to compute the expected value of the training data, what we have now, given the parameters of our model, and now we want to change the parameters so that we get closer to what we want to achieve. Okay. So I want to find the maximum of the probability, so I can do that using gradient what? Ascent. Very good, right? So I can do that with gradient descent. The only problem is that computing these above functions, right, above meaning these functions that we've derived here, it's a little slow. You can do it, right, which is quite slow, okay? So people don't do that. Instead, it is convenient to use a lower bound for these functions. Define a lower bound, which we're not going to do here, but I'm just going to give you one possible bound to use of these conditional probabilities, and then work with that. And that gives you an approximate solution. Which actually works well and is computable in a reasonable amount of time. And as you'll see in the paper I posted in Canvas, they use the known bound that the log of the probability is actually not equal, but larger or equal to this lower bound, which is V. Remember, V are the observable inputs. Capital W, which is the matrix or the tensor of the weights between the first layer or the input layer and the first hidden layer, right? So you can write this as 1. Mu1, I'm going to define mu's in a second, plus mu1 transpose W2, whoa, W2 mu2 plus mu2 transpose W3. This W, capital W, the matrix or tensor of the parameters, minus the log of the z function. Remember, the z function is a normalizing constant of the Boltzmann probability or distribution, and plus h, just going to do a weird h here, is h function. Now, this h function is nothing else than the entropy function of the lower bound. So don't worry about this, but just so that you know, this is the entropy function of the, actually not the bound itself, but of the function used to compute this lower bound. Okay. This we already know, and these mu's are obviously the mean field parameters, right, that need to be computed between the layers. And how do we compute them? Well, we compute them with the equation that we have been using until now. So let's write it down. So we have mu j, okay, mu j of 1, right, for the first layer is going to be given by g of the sum over all I of wij. This is the ith entry of the matrix W1 times vi plus, okay, what else? Plus L of, anyone? Would it be in the second term? Same thing that we've been doing until now. So this is the weights times the input, and this the weights. So W, where is it going to be? Lj, right? Times the next result, which is going to be another mu, right? So it's going to be mu of L for the next layer, right? So this is 2 and this is 2, as we did before, right? Same thing that we did before. Okay? And that's for the first layer. And now let's rewrite this for the second layer. Same thing. G of the sum of overall j of wjl mu j. This is for the first layer plus the sum over all k of wlk mu k for now the third layer, right? And how about mu k of the third layer if I only have 3 layers, right? If I assume here I only have 3 layers. So for the third layer, this is going to be g of what? Anyone? Let's say L. What's this going to be? Come on. W of what? KL, okay. Of which layer is this? 3, okay. And that this is multiplied by mu L, very good. And that's it, right? Because that's the third layer, right? There's nothing else. Okay. And again, let's assume that this G is a logistic regression, the logistic sigmoidal function that we've been using. Okay. So now the algorithm is just an iterative way, right, of computing the weights with gradient descent and the mu's with that algorithm that we have here, right? And then you iterate the two until you converge to a maximum of probability, right? So you do gradient descent. Yep. Okay, so now I want to go back to what we had in our last lecture of low-level vision. And remember that we had a set of images of naturalist scenes like this, and we extracted random windows from these naturalist scenes, right? And then we put them together, and then we did the PCA. And if we did the PCA, this is the basis set of basis that define our feature space that describe naturalist scenes, right? And then if we use the sparse method that we talk about, we get this other set of basis vectors which resemble Gabor features, right? Or Gabor filters, rather. So now what we can do is we can define a deep neural network, like what we've done here, right? And see after the first or the second layer what these nodes in that network represent, right? In the same way that PCA solve for linear least squares. This first layer solve for a nonlinear version of least squares, and the second layer solve for another nonlinear version of least squares, right? And if you do that, then for that Boltzmann model that we have defined here, this is what you get in, say, the first layer. These are cells, and you can see here things that resemble Gabor filters as well, right? And other more complicated things. And there is color here because the images that were processed were in color, which means that in that case, if you want to do it that way, you need to use that tensor algorithm that you have in your homework, right? Because an image, it's a matrix, right? So that window can be treated as a matrix. When you have color images, you have a tensor because you have a matrix copied 3 times, right? So you have a new dimension. So you have a 3-ordered tensor. And if you do it for these tensors and you solve with gradient descent, this is the result for a set of random naturalist scenes of the first layer, looking like Gabors and some other weird frequency things. Second layer, they are not really Gabors. They are more like some snippets, some snakes, if you will, some curves that look like Gabors as well, right? So like curved Gabors and some other more complicated functions. And then the higher you go into the layers, the more complex representation we have. So we'll talk about these higher level features later in the course. But for now, I want you to focus on these first and second layer features. And we'll be using those constantly in mid-level and especially in high-level vision. And these are called deep features, right? So we'll use Gabor filters or other wavelets to represent our images or patches of our images. We may use just the patches themselves. We may use a PCA representation of those. We may use an ICA or a sparse representation of those, right? So all the things that we've seen here. Or we may use deep features like these ones, okay? And all of these options are options for low-level vision of how we're going to represent our images from now on, okay? And that is the most important message that we have given to date, right? You have to understand that low-level vision is all about extracting representations for mid-level and high-level vision tasks, okay? And these are many ways of doing that with Gabors, with least squares features, meaning PCA, with sparse features that we have defined here, which would be an L1 version or some other sparse norm version of least squares, and with nonlinear least squares, which is this last one, the features that we have discussed. Okay? Any questions before we move on? No? You sure? Okay, so since your homework is due tomorrow, we'll have a project on some of this following up. Okay, maybe we can do the PCA and the sparse features, for example, which are the simplest ones to work with. Okay, we'll give you plenty of time for that one. Don't worry. Okay, so back to the lecture then. Okay, so as we transition from low level into more mid-level vision, I want to spend a little time talking about tracking. And tracking refers to the consecutive tracking of a specific objects or fiducial points in an image through time. Okay? Because vision, obviously, as you know, doesn't usually apply to a single image. I mean, obviously, we do a lot of computer vision in a single image because computers just basically store images, right? Or to this day, images has been the preferred type of storage. But vision in reality, in the real world, animals use a sequence of images, right, a video sequence, to process and extract information, process the image or the scene and extract information from that scene, right? So we're going to be using that quite a bit. And for this, you may want to use a tracking algorithm. And the idea of a tracking algorithm is that once you have used low-level vision to detect these unions that we have defined, say corners, right? L unions or T unions or K unions or what have you, or some other features like Gabor, where the Gabor filter, so you filter an image with Gabors, there are going to be points that are maximums of that process, right? Of that of that convolution. Then those fiducial points are also relevant, right? Or can also be defined as a fiducial points of interest. So all these points, you can either track them across multiple images, right? And we have a way to do that. Anyone can tell me which way or which algorithm I could use, or which algorithms, we've seen at least two, which algorithms I could use to track or determine point correspondences between two or more images? Anyone? Very good, right? SIFT, what was the other one? SURF, okay, good. So these are some of the algorithms that we can use, right? So obviously that's one way to do it. So let's write this down as probably as in a schematic here. So here's what I'm going to do. So for example, imagine that I have a set of images, right? A video sequence. And a video sequence is nothing else than a set of images. And say that in each of these images, I extract some fiducial points or points of interest. And I don't know, maybe these 4 here and these 4 here, right? And then if I do this with SIFT, for example, then SIFT is going to give me some point correspondences, right? So it's going to tell me, OK, this point corresponds with this one, and this point corresponds with this other one, and this one corresponds with this one, and this one with this one, right? That's what SIFT is going to do, right? Or any of these other methods. The other option that I have, which is what tracking will do, is that I have the same set of images defining the same video sequence. And now I extract some points of interest in probably just the first image, maybe the first or second. There are variations for that. And then around each of these points of interest, I extract some window, right? And then I define that window as a window to be tracked across video sequences, right? So I want to know that these windows correspond to these other windows here over time, and that there is this correspondence, right? That this one corresponds to this one here, this one has moved here, this one has moved there, and this one has moved there, for example, right? Okay. And what we need to do is to have an algorithm that's able to track the trajectory of these points or how these points move across that video sequence. Okay? So far, so good? All right. So that's a problem definition. Now let's see how we can do that. So generally speaking, we have two different types of tracking algorithms. One would be using classifiers. So it's just going to call them, I know, classifier-based methods. How about that? And the second one is generative-based methods. Classification methods, and this is something generic of machine learning and computer vision, classification-based methods are binary by nature. Okay? A classifier can either detect or not detect the presence of an object or fiducial point of interest in a location of the image at a time, right? It can detect it or not detect it. So it's a binary decision. So let's say that I'm looking for a specific fiducial point of interest that I have detected in the first image, this one right here. And now I built a function f that when I apply to every location in this other image, that function f gives me 0 everywhere except 1 at one location, which is the location where this point has moved to, right? That's a classifier. Now, there are a lot of classifiers that you can use. Again, you have to take the machine learning course. Dozens, hundreds, potentially thousands of potential classifiers that you could build, right? That would achieve this. And then there are generative-based methods. And generative methods means that you learn a model. So that function f, it's actually a model of what that window around that point of interest actually represents. And then what you're interested in is to apply that model that you have learned here and see which location of that image is closest to the reconstruction that your model can give of that window, right? So let's see that more formally to see how this would work. So let's start with an image like this. And let's say that I have a point of interest here that defines me a window. Maybe I have another point of interest here, finds me another window, and so on, right? Another point here. Now, for each of these points of interest, I get a window like this. right? So this one would be here, here, and here. I'm going to call these the targets, okay? So let me call these maybe capital, actually, let me write it here. Capital T1, capital T2, capital T3, okay? So that I can write all of them as capital T. It's my vector with T1, T2, and so on. T, actually, I said 3. That makes sense. T, let's say M. M. Yeah. Okay. Now, I have to create a model for each of a model that works for each of these different targets that I have. Okay. Now, to do that, what I'm going to do, I'm going to extract some windows here, right? Maybe like this, for each of the targets, okay? So let me call these windows, say, for the first one, I'm going to call it, I'm going to call them D11, D12, D13, and so on up to, say, D1K. And then for the last one here, right, when I extract these windows, this I'm going to call them DM1 through DMK. Okay? So I can write this down as a vector. Let's call this vector D1. Let's call this vector DM. Okay? So now I can construct another matrix here, capital D, where I have D1, DM as my sub-windows here. Now, note here, obviously, that each of these DIs is given in, say, K, RK, and therefore capital D will be given in K times M, right? Okay, so now if I want here to identify where my targets have moved to, right? My Xi's here, right? Or let's just say my X. Then what do I want? In a generative model, I want to see how well I can reconstruct the observation. And how do I do that? Well, I have X has to be given to D, these different windows that I have extracted from all my targets, times a tensor or matrix of corresponding coefficients. Okay? So I'm just computing a linear way to compute a reconstruction, right? Now, in this model, this D, these small d's, I'm going to call these small d's the templates, okay? Or small templates, if you prefer, a window of the templates. And capital D, this one, we're going to call the dictionary. Because the idea is, how can I reconstruct X as a linear combination of the elements, the templates, in my dictionary? You see how this works? Yeah? So far, so good? OK. So how am I going to compute this? Well, we can use linear least squares, for example, right? This is also called, generally in computer vision, you'll see this called the reconstruction error, right? Which is given as, let's see, I want to minimize, right? Linear least square, so least minimize. I want to find the parameter z that minimize 1/2 of x minus dz, right? And for some norm, I'm going to use a Frobenius norm because it's the straightforward extension of the 2 norm for matrices, right? It's not the 2 norm for matrices, but it's slightly different, but has nice properties. So it's easier to work with. So here, F represents a Frobenius norm. So that's our first solution, right? Very important. Our first solution, just using linear least squares to find the parameter z that best reconstruct us, right? Now, to localize the landmark points here, what I'm going to find is at which location I can reconstruct best, right? And whatever is my best reconstruction, that will be my fiducial point. Okay? All right. However, I can easily extend this solution by imposing something else. Imposing, yeah, question.
Does this assume that all the points are present in all this maps have different PNs? Let's say one point is present only till ti, where I is less than n, or like I equal to n by 2. So can you even track if the points are not present in all the snapshots?
So here's the deal, right? If you use this, you're using all the DIs that you have extracted from all the targets. But that's not what you want to do, is it? What you want is you want to use a small number of them, the ones that specifically define your target, right? And how do you know to do that already? By adding a requirement that z, the coefficients, be what? Most z's, right? z1, z2, z3, all these coefficients have to be equal to, right? And just a few of them should not be 0. And that's called sparse, right? So what we're going to do in our second solution is to add a regularizer to the least square solution, the reconstruction error, to impose a sparseness, right? So we're going to have, we're going to minimize, going to find the z that minimizes the reconstruction error plus some regularization term lambda for ZA. This is the norm of Z, and A, it's some norm that measures the sparseness in your tensor, okay? In your vector, in your matrix, in your tensor in general. Typical choices for that A, typically you will see people using the one norm because it imposes a sparseness, although it's not the only one. I'll talk more about this in a second. It's not the only one that imposes sparseness. What else? In some cases, you will see also that people use, instead of the one norm, the PQ norm. And this is the definition of the PQ norm for my matrix Z, PQ. It's given, whoops. OK, let's start here. The sum over all I, the sum over all j of all the elements ij of my matrix Z, right? That means the ith row and the jth column, right? To the power of p, and this other one to the power of q over p, and then all over 1 over p. I'm sorry, 1 over q should be, right? P, q, yes. Q. OK, makes more sense. Yes? OK. So that's a much preferred solution, right? Because you want to impose that sparseness. Now, what is important to really important to note here is that this dictionary that we have defined can be changed or defined in a number of ways, right? Anyone can tell me what other elements, the d sub i's, could I have as elements of my dictionary? What's that?
The shape or the orientation of geometry?
Things that we have kind of seen already. I guess you could use some edge detection, if that's what you're referring to. You could try to do that. Not sure that would work. But what else have we seen? Kind of something I said is like the most important thing we should have learned. That's a really good guess. No, but you could use, instead of those, to reconstruct your image, you could use the Gabor filters, right? Or the responses of the Gabor filters in the target windows, right? Or of any other wavelet. Or you could take the target and extract these windows and do a least squares analysis of this, meaning PCA, right? And extract these basis vectors as the elements of your dictionary. Or you could extract a basis set that is a basis set of a sparse basis vectors, right, to define these dictionaries. Or you could have a deep neural network to analyze all your targets and extract deep features and use those deep features as elements of that dictionary. That's the beauty of low-level vision. You can use now all of these things that we have learned to add in any other algorithm that we're going to define as alternative to represent the dictionary or the templates that will describe our mid-level and high-level vision tasks. Okay? Question?
So Z should be user-defined, right? Like
Z is just it's a tensor of coefficients, right?
Yeah, so we have to like first analyze these snapshots and say whether this object is present in each image.
Well, this is not necessarily an object. It's just some point of interest, right? It could correspond to an object. It could correspond to a corner of an object. It could.
It basically denotes whether it's present in the different windows or not.
So these are the targets in green here, right? In red, you have a way to describe a dictionary that gives you basis vectors to define each of the targets, right? Now, how you define that dictionary, it's up to you, right? This dictionary could be literally the pixel values of these windows, could be the Gabor filters or the filtering with wavelets of these targets, could be a PCA analysis of windows of these targets, could be a sparse basis set of vectors from these windows of the targets, could be Div features could be anything that you want to use.
I mean, I'm asking about Z, like, so that's like, it's ones and zeros, right? That's what you said.
You want it to be sparse, right? So you want it to have mostly zeros. Doesn't mean that the other ones are going to be ones, just going to be some value, right? Whatever value minimizes the reconstruction error given by the least squares function, error function. Okay. Any other questions? Okay, so that's what we are going to do. If we want to track points in low level moving into mid-level vision, we are going to either use methods like SIFT and SURF and the like that we have defined here, right? Or we're going to have a method that allows us to define templates based on some dictionary, right? That is able to track points across a sequence of images. Okay. Now, if you want to use, which is preferred to just using windows here of pixels, right, which is the simplest way, you may want to use, say, PCA or a sparse representation, which will take you to ICA, independent components analysis, which I cover in detail in the machine learning course, if you're interested. And again, all the lectures are on YouTube, so if you haven't taken the course and you don't want to wait until next year, and watch it right now. But one of the problems that you're going to face if you use PCA and ICA is that these methods are based on linear least squares, or actually least squares, which means that what is least squares is f of x equals x squared, right? That's the squares. And what happens with this is that if we have outliers, the square is going to make them very relevant. And these are actually outliers that you don't want to consider in your data, right? So let's see a few methods of how to address outliers in PCA, and I'm only going to cover PCA. ICA also has methods for this that you should be able to follow relatively easy from here once you know the ones for PCA. Okay, so robust PCA. How are we doing? Okay. Let's do at least the problem definition. So the problem with PCA is that it's very sensitive to outliers, right? And this is because if I have f of x equals x squared, this function looks something like this, right? And then the inliers are going to be here, right? And here, and the outliers, the points that I don't want to consider, are going to be out here, right? And the problem is if I have a point here, this is an outlier, because of the x squared, it's going to have a tremendous relevance in my error function here, right? And I want to avoid that. So to solve this problem, we can assume, or we usually, I should say, assume that our matrix, say capital M, is given as the sum of the desirable low rank matrix is the sum of some desirable low rank, and this is the keyword here, right? That's why we use PCA, because there is a lower rank representation of our data, right? Remember? That's what the correlations that we talk about actually define, right? Matrix L and some noise matrix, say S. Okay? So formally, I can define this as M is equal to L plus S. So, okay, now we need to define, as we did before, a method to find the global, or if we cannot find the global optimum, right? At least some local optimum for this equation. And as usual, we can define our famous criterion by now. We want to minimize the norm of L, right? That's our low rank matrix, and we assume that therefore we want to minimize that that norm, and we want to regularize this with some other norm for S. Now, because this is based on the reconstruction of M, what do we want to do? We want to use the square norm, right? The 2 norm. So here, typically, A will typically be the 2 norm. Maybe also it could be the nuclear norm. I'm going to define the nuclear norm in a second, or maybe next time, next class if we don't have time here. And then B, this B here, has to be a norm that promotes sparseness, right? Because noise is going to be sparse. We know that. So we already know how to do that. So B could be the 1 norm, right? It could also be a quasi-norm. Or it could be the so-called, I'm going to put it in quotation mark, the 0 norm. Now remember from 5460 that this is the 2 norm, right? The 2 norm defines a circle, meaning all the points in that circle at the same distance given the 2 norm, right? The 1 norm is given by the rhomboid within that circle, right? And a quasi-norm is going to be something between this and the 0 norm, which is something like this, right? So if this is P, P a quasi-norm, then P could be between 1 and 0, right? So actually the other way. Between 1 and 0, right? So it has to be larger than 0, smaller than 1, right? Remember, quasi-norms satisfy all the properties of a norm except for the triangle inequality that's given up to scale. Now, I put the 0 norm in quotation marks here because the zero norm, it's actually not a norm, doesn't satisfy the properties of a norm, so it's not technically a norm. All we do in the zero norm is we count the number of non-zero entries in our vector or in our tensor. Okay, that's it. The number of non-zero entries. And when you want to minimize this, what you're maximizing, you're guaranteeing that the number of non-zero entries is as minimum as possible, right? So it's the extreme case, the zero norm. Reasons why the zero norm is usually not used is because it's not non-differentiable, right? So if you want to use gradient ascent or gradient descent, we're going to run into problems. So instead, you may want to use a quasi-norm. It's a much better option, and one that I've used with greater success in the past. OK, I'm going to talk about the nuclear norm next, and then give another possible solution or two for robust PCA, and then we'll dig deep into mid-level vision, and we'll start with the projective space, which is an extension basically of what we did in introduction to image processing computer vision in 5460, but now with the projective space, which is a much cooler set of tools that going to give us much better solutions to our problems. All right, I'll see you Thursday.